Give it a minute, it should expand. Or if you, the one next to the plus sign, maybe in your case, the one next to the plus sign.
That is what I did. That is what I did now. Okay, that is what I did now. And this is what I got. I do not know. Just give me 1 moment.
Okay, you just click on that. Just click, sir. Just take the slide. Start the slide. Please take the case study slides. Just click on the case study left. Just go left and click on the case study slide.
I'll do that.
Just click on that. And you see on the left hand side, you've got a cross sign. You just switch off that. Click it off, sir. Switch it off. Yes. Okay. And now if you click the slideshow button next to 74, you will fill the page.
Is
Go
it
down.
all right?
Yeah, next to 74, there's a go down. So next to 74, there's a slide. Then that one, click that. Click.
The one that brings to the full screen, no?
That's right.
This is it. Nothing is happening.
It's rather small. Okay, right. So you carry on. Carry on.
Yeah, carry on. It's visible now. You can start.
Okay, then as a case study, we are taking this 45.7 meter girders. As I decided the components, as we decided the components of 45.7 meter girders are I-beams, built-up beams, star angles, and T-sections. So we'll deal one by one. We'll deal with how they are welded. Just 1 minute, just 1 minute. I'll do one thing. Someone has come, I'll just take his support and see if I can fix it.
Right.
Let's see Subrat if we can do something. Can you see the full screen, Dr. Subarao?
No, sir, it's not filling the full screen. In fact, your yellow down below, that yellow should not be there actually on that one. You are choosing that. It shouldn't be on that.
Shall I exit and come back again? Will it be all right?
I
think I'm exiting and coming back again. Okay.
Okay, sir. Well, we'll give a minute. Go ahead.
Okay.
Go ahead. Just bear with us. A small issue. I think Jana will relaunch, and we will get back to this discussion on fabrication with a typical case. There you go, sir. Perfect.
Okay.
Perfect, sir. Just go back so that we can start from the beginning, and let us start from the first slide.
Okay.
Right. That's fine. That's fine, sir.
Okay. So today our today's topic is fabrication. As a case study, we'll take a 45.7 meter span, and there are several components. There are I-beams, there are built-up sections. So all these sections have a typical welding parameters, welding sequence, welding procedures. That is why this particular span will give us an insight into what are the precautions and what are the ways we should fabricate this any steel girder. You'll almost have everything. These are the joints. These are the joints of a 45.7 meter span. These are several joints. At one point, it is a vertical. Then it is a sway bracings. Then different diagonals, how they are connected. These are basically, this would be required at the time of making layouts for drilling, because the drillings, if there is any error in drilling, ultimately we will have a big problem in achieving the proper camber. So the layout drawings and preparing proper jigs and fixtures is very vital to achieve the camber of this particular girder. This is the basic concept of girder. We basically want that all the bridges should have a positive camber. Positive camber has the advantage on application also the girder levels out and assumes the design shape. The span returns back to the positive camber. So positive camber is an absolute necessity for any steel bridge. This is what happens in the negative camber. Then this is the layout for the camber diagram of 45.7 meter span. There are two types of layout here, two types of markings. One is called a nominal layout. One is called a camber layout. What is the difference? Nominal layout is the layout of the girder as per the drawing. But at the bottom, we have the camber diagram. That means it is supposed to achieve the camber at the center. There are four. There are L0, L1, L2, L3, L4, and there is a mirror image on the other side. So L4 is the joint where we are having a camber of 53.6 millimeter. And at L1, we have different camber. This is the required camber. This is the design camber of this particular girder. In order to achieve this camber, we have to shorten the length of the components. So the red marks which are there is the actual fabrication length of the components. And the nominal camber is what the bridge is supposed to have when it is fully loaded. This is the length that is to be achieved by each member. The black one is the length that the bridge theoretically should achieve. And this camber in the red is the actual length of the component that needs to be fabricated. So unless we have this, if you have a little bit of error in fabrication and we do not achieve this length, then we will miss the camber. Important documents. What are the important documents that are required during the fabrication? The documents are quality assurance plan. Every fabrication starts with a quality assurance plan. Then we have welding procedure qualification record and welding procedure specification. These are the most three important documents for any girder fabrication. Quality assurance plan. Quality assurance plan, basically what we have to do is we have to assure quality at several stages. One is raw material, second is during the work, and third is during the manufacturing process or during the work, and the third is at the time of assembly. Also, if we take the first component, raw materials, we need to find out what are the components we'll be checking. Let us say for raw materials, where the steel plate has come, from which manufacturer it has come, characteristics to be checked. The material condition when it arrives, the dimensions, the mechanical, the physical properties. Then mode of inspection. What are the mode of inspection? Like let us say when you receive metal, we look at the correlation. Correlation means you have to find out what is the TC, what is the heat number, so that we can compare whether the plate or the structural belongs to the same heat number. Then the quality. Quality is what are the type of plates you have received, whether there is a fitting mark or not, what is the UTS, what is the lesson, etc. This comes from the material test certificate that comes with the material. Then here, which is with the extent of checking, who is got what responsibility, like fabricator has 100% to check, and the inspecting authority, what percentage they have to check. What are the reference documents? Reference documents for this particular item is the manufacturer test certificate, which comes with the material. Then what are the acceptance norms, whether it's grade B or E250 or E350 or E4, whatever the grade, whatever is designed, whatever is given in the drawing, those acceptance norms. Then our formats and records. If it is a IRS B1 2000, these are all particular documents which can be specified by the manufacturer. Then the remarks. Similarly, for all other activities like fabrication, like during the manufacturing process, what are tests we have to do, what are the characteristics we must maintain, what is the extent of checking, Similarly, for every component, every stage of fabrication, all these components are to be mentioned in this document. Then welding procedure qualification record. Welding procedure qualification record is a very important document in the sense, welding procedure qualification, when you are trying to do a welding, first we have to find out whether the particular type of welding we are doing gives us the right amount of property strength, and are we achieving a target. For that, what we have to do is, we have to take samples. Let us say we have to do a particular butt welding, or we have to do a fillet welding. And we say that this particular fillet welding is to be done with a submerged arc welding. Then what we have to do is, we have to take identical thickness of the plate, prepare a joint and weld it. And in the process, we have to do several times, we have to prepare several samples, weld it with different parameters, like weld it with different voltage, current, the wear speed, the feed of the welding, to achieve the right kind of bead. And then we have to test that piece. If that piece passes all the tests, then that particular parameter what we have set is the welding procedures qualification. That means we have qualified that procedure of welding. So in that, what we have to do is, what are the requirements, what are the parameters, or what are the things? We give the name of the welder, we give the date of the prepared test piece, dimension of the test piece, then the welding process. Welding process means whether we are making it submerged arc, whether we are making metal inert gas, or whether we are making gas metal flux code FCAW, flux code arc welding, or whatever the process that we choose. Then what welding position? At times, welding position, either we are downhand, other we are doing it vertical, other we are doing horizontal. Whatever the position of the welding has to be done, that position has to be mentioned. Then we need welding current. At what current we welded that particular specimen, and weld joint details. What is the type of welder? Welding consumables. Every consumable of the welding, it has got its own specification, own BIS number. On the basis of welding consumables, identification of welding consumables is done. Then we have something called a polarity. What is the polarity? Actually, this is when we do a welding, we have an electrode, we have the job. When you give there are two types of polarities. One is DC electronegative, DC electropositive. What is the importance of this? I'll come to that. It's a very important thing. Sometimes what happens, suppose we have to weld a particular I-beam, and by mistake the welder connects the negative, because normally we have a concept that it is a negative, the negative is called the electrode, and the job is called the job is supposed to be positive. If it is connected that way, then you don't achieve the right kind of weld weight. The reason being, so this particular, when we do the welding, we have to mention whether we are getting the right kind of weld bit by connecting the welding rod electrode to the negative terminal of the power source or the positive terminal. So it is mentioned DCEN or DCEP. That means whether it's a straight polarity or it's a reverse polarity. Straight polarity means electrode is connected to the negative. Reverse polarity means electrode is connected to the positive. Normally, in all MIG and all submerged arc welding, the electrode is always connected to the positive. But in case of a TIG welding, which is mostly in case of stainless steel, the electrode is connected to the negative. Because what we want there, we want the maximum heat to go to the wear. But in this case, because the thickness of the plate is more, we want a maximum energy to be concentrated at the plate material itself, so that right kind of fusion takes place. So this polarity is equally vital as our other welding parameters of current and voltage. So what we do here in this tabular form, we have the important parameters. How many, let us say we have a 12 millimeter welding. In how many passes we do the weld? 1 pass, 2 pass. Sometimes the welding thickness is 20 mm, 25 mm. Maybe we don't achieve it in 1 pass. How many number of welding passes we make? What electrode, what diameter of electrode we have given? What is the current? what is the arc voltage, what is the wear speed, what is the travel speed, what is the electrical stick out, what is the gas flow rate in case of MIG, it is a gas flow rate. In case of submerged arc, it is flux. No flow rate of flux is mentioned. Once we do a particular welding with all the parameters, trial parameters, these are all trial pieces. After all the trial pieces are done, then we go to the tests. We do all types of tests that is required, like non-destructive testing, like destructive testing. So every test is conducted on these test specimen. If the particular test specimen with its all the characteristics of welding, when that passes, we call it welding procedure qualification record. Once this record is done, then we have qualified of the procedure. Then next is we come to components. Then we have a WPSS, welding procedure specification sheet. Each component, let us say we have an I-beam, then we make one procedure sheet for the I-beam. Then if you have a channel, we have one procedure sheet for every component has a procedure specification sheet. In that case, we mention with the client whatever we have fixed in the welding procedure qualification records. All those parameters are mentioned here, and each component is checked with that parameter. Like let us say number 4, we have welding process. First, base metal. What is our metal that we are welding? What is the type of the plate that we are welding? This comes from the material specification. Then what is the weld joint? Fillet. This is the fillet weld joint. This is the what type of base material you are using. What is the welding process you are using? What welding position you are using? Flat welding position. And what is the electrode that we are using? Consumable welding consumable that you are using. Either the wear classification, the flux classification. If there is no shielding arc in this particular case, because the submerged arc welding, no shielding gas is required. Then the base metal preparation, how you have prepared the base material, whether how you have cleaned it, you have not cleaned it, how you should clean it, that is also mentioned. Then joint design detail. That means this particular gives what are the joints and what is the thickness of the weld, what are the dimensions of the weld, and what is the dimension of the component. Like here in this particular case, the dimension of the weld is 6 millimeter. Then we have position of the runouts this here. Then we have the welding parameters. This is a very vital thing. Welding parameters means we have, as I had told you earlier, that during qualification we have said this particular weld has to be done in how many passes. Dimension of the electrode, voltage, current, everything is mentioned. That means this component is required to be fabricated or welded in this particular with this particular parameters. Then then let us go to material properties. Material properties, see, basically all the fabrications are done on the basis of the steel as per the IS 2062. So IS 2062, normally nowadays most of the steels are BO, but the grades of the steel that are available as per the IS 2062 are A, BR, BO, and C. These are the normal grades of for every grade of steel. There are 4 other classification, 4 types of the steel that is available. One grade is impact test is not required. There is no Charpy impact test in grade. This is semi-killed steel. Then BR is impact. No, this is wrong. BR is impact test optional if required at room temperature. BO is impact test mandatory at 0 degrees centigrade, and C impact test is mandatory at minus 20 degrees centigrade. This is the requirement as per the IS 2062 grade B. This is the chemical composition of IS 2062 grade B. We have here 9 grades. 9 grades start from E250 to E650. So each grade has got again 4 classifications. 4 classifications. These are the carbon, manganese, silicon, phosphorus, and this is the maximum. This is the maximum that should. This is certain lateral analysis percentage maximum. So once we take E250, that means the maximum carbon that should be there in that particular steel is 0.23. And if you take BR, it is 0.22, BRBO 0.22. That way, all the composition, all the components or all the alloying elements of the steel are mentioned in the chemical composition. So this, if you see the mode of oxidation, most of the mode of oxidation, if you see, A and BR can be semi-killed and killed. What is the meaning of semi-killed and killed steel is here there's a mention of it, but anyway, we'll skip that. But if we are ordering for grade C, then it has got to be basically, it has to be killed steel. For any of the designation grades, wherever grade C is there, we got to make it, got to roll it from the killed steels. This is the carbon equivalent of the parent material. This carbon equivalent is a very important component when we are welding a particular material. What is the meaning of carbon component? Carbon component is an empirical number which, on the basis of which we can predict whether a particular steel is weldable or not weldable. And this carbon equivalent for a particular steel, then this is the calculation where it says the percentage of carbon, manganese, chromium, each component, each alloying element is in this particular formula in this empirical formula. On the basis of this, we find out the carbon equivalent, and this carbon equivalent predicts how weldable the steel is. See, if as per the practice, as per the experience, if carbon equivalent is up to 0.35, the weldability is excellent. And if it goes on up, then the weldability is poor. That means you just cannot weld a steel as easily when the carbon equivalent is 0.35 as the carbon equivalent is 0.5. When it is 0.5, the welding of the steel is difficult. Either you have to preheat it or you have to take other procedures and then only heat it. Otherwise, the welding, and during welding, it will crack. The carbon equivalent here is, let's say, grade 250 and grade 8. The actual carbon is 0.23, but the carbon equivalent is not 0.2 because all these components contribute to the increase in the carbon component. And when we say a particular, this is the carbon component, actually it has a very carbon equivalent. Carbon equivalent means this particular steel will behave to a normal carbon steel of 0.35%. That is as per the iron carbon diagram, but whatever it is, for our purpose, the low carbon equivalent steel is more weldable than a higher carbon equivalent steel. So this is the carbon equivalent comparison up to if you have a higher carbon equivalent, then up to 41065 we need preheat. From 253 need preheat only because of the thickness of the plates. So carbon equivalent is a very significant factor when we are finding out the steel, welding in steel. These are the different welding rods and their classifications as per the IRS P1. So depending on when you buy a wear or when you buy a flux, you mention what you are going to, what flux and where you will be going. And it will depend on what is the type of welding you are using, what is the class, purpose of use, what is the class, depending on the class, what quality of the weld has to be there. Then accordingly, you make the mention in WPSS and WPQR. So the welding class, on the basis of the class, one has to select the wear and select the flux. And these are all this wear and flux come from standard companies. Once we mention that this is the wear and the flux and this is my class of the welding companies will give you. And because once you order it on that company, there should be IDSO certified or your client, whoever is, his certification would be required. Because this particular class is given to them on the basis of the test of their product. This is a batch certificate of ISAB, just to indicate how, when we are taking a soft flux, so how they mention all the properties of the weld. And they also at their end have done the welding and done all the analysis, physical and chemical analysis of that particular weld metal with their grade of flux and their grade of wear. So this certificate would also be required to be submitted at the time of inspection. Then coming to drilling, as we had discussed earlier, that when you are doing a girder, drilling is a very vital thing, because unless the drilling is properly done, the orientation of the hole is properly done, there will be a tremendous problem at the assembly of the girder, and most likely we may not achieve the camber that is required if there is an error in drilling. So let us say we take one component of the 45%. Let us say this is the top cord. If you see at the end here, this is called an end breaker. This is the top cord. This is the diagonal, and this is the vertical. There are so many components which are getting assembled in one place, and all the hole directions are all in different directions. And maybe this particular point, these components are shortened. Then how do you drill the hole accurately? Because our drilling of the hole, accuracy of our drilling of the hole will allow us to achieve the right camber and the right requirement of this particular girder. So what we do is, this is a very complicated joint. To achieve, let us say we have several spans. Then how do we do it? Then we go for the proper jigs and fixtures. These are jigs and fixtures. So on the right side, we have jigs. These are on the layouts. These are prepared on the basis of layouts. Once they are prepared on the basis of layouts, then there are hardened guides which are welded, and this particular component is checked again and again. And on the basis of this, all further templates are done, and on the basis of templates, all drillings are done. That means we make a zig. Jig is basically for dealing on the everyday basis. Template is there, which is kept as a check for the jigs, intermittent check of the jigs. Because when you start drilling the jigs, the holes wear out, then there will be a shift in the holes. But template, once they are prepared as per the layout, these templates are preserved. The templates are preserved, and they are checked from time to time with the jigs. And jigs are the main markers on the basis of which the drilling is carried out. So how do you make the jigs? As we had discussed earlier, the detail length of the girders are taken on the hole load. The hole positions are marked into the templates. Jigs are prepared from the templates to carry out the drilling in exact location in the component. The jigs allow repeatability and accuracy. These are the purpose of jigs and templates. First we make the template, then we make the jig, and subsequent fabrication of every gusset is done on basis of jig. And templates are kept to be checked intermittently and to be checked by the inspectors. Then nowadays, many of the clients are insisting on CNC machines. Earlier, there are many methods of drilling. We had radial drills, we had magnetic drill bits. Even those are also in use today. And many fabricators are also graduating into CNC drills. Many CNC machines have come into the space of fabrication, and people are updating themselves. So CNC drills are becoming very common nowadays. So this is how a CNC drill works. Everything is computerized, the whole layout, etc. Then when we are doing the CNC drill, maybe we don't need jigs anymore, because the location of the holes or the orientation of the hole is directly read from the CAD drawings, and then it is fed into its CNC system or the controller, and the controller positions the welding drilling the drill bits, and the drilling is done as per the CAD drawing. Then coming to how we start fabrication, we start fabrication with the process of cutting. And cutting starts with, there are several processes of cutting: oxyfuel cutting, plasma cutting. Nowadays people are going for laser cutting. And next is searing and punching. These are for angles only. Oxyfuel cutting is a very common process where you use oxygen and fuel for heating and cutting the plates. Plasma cutting is again plasma is through. There are two types of plasma: air plasma or CO2 plus oxygen plasma. So this is a process where we don't need any consumable like fuel for cutting. Laser cutting is again a process, a very fast process. Plasma and laser cutting are very fast processes. Oxyfuel cutting is much slower, but it's a very proven thing. But nowadays, when we are going, some girders are now coming with stainless steel. The stainless steel plates cannot be cut with oxygen and oxyfuel cutting process. It basically needs plasma and laser because stainless steel doesn't oxidize and we cannot cut stainless steel with oxyfuel cutting process. This is oxyfuel, and nowadays machines come with both the torches, oxygen, oxyfuel cutting and plasma cutting. The advantage in having two of these different type of torches is when we are using plasma cutting and we want to cut very thick plates, then the machine becomes very expensive. So normally people up to 20-25 mm prefer to go for plasma, and higher plates are cut with thicker plates are cut with oxyfuel. Then let's go to welding. What are the different types of welding? One is shield metal arc welding, or what we call stick welding. What we normally see every fabricator has been uses or were using earlier was stick welding. That is called submerged shield metal arc welding. Then we have gas metal arc welding, which we call MIG. Now MIG is a process where you have you use a gas, either carbon dioxide, argon, or mixture of argon and carbon dioxide, shielding gas. And the electrode is in shape of a wire. It's not in shape of a flux coated welding stick. And then we have submerged arc welding process. The consumables in submerged arc in SMAW is butyl coated electrodes. Electrodes we have seen that it's got a cover. In the gas metal arc welding we have shielding gas. In SAW where we have flux. Flux gives the protection against corrosion, and it gives a protection for the welding when it is in a very hot condition. And this is submerged arc welding process, and it's got the top cover, the flux that is used that gets covered on the top of the hot welding metal as a slag, and the slag is removed subsequently after the welding. Then the member that when we are discussing 45.7, these are the type of members and the type of component, the structure that has to be done, and what is the weld that is required. Let us say the bottom cut, it's a fillet weld. Most of this is a fillet weld. We normally do not have butt welding in this particular girder, because we need a butt welding whenever the components are pretty long and we do not have the length of the plate for that fabrication. In that case, we have to do butt welding, but most of the weldings are fillet. This is the fillet welding, and this is the butt welding. Butt welding means when two components are butting. This is mostly not required in this basis because no component is more than 12 meters. So we get plates straight away for 12 meters. But wherever sometimes we come across girders when the girders are 13 meters, 13.5 meters, and we don't get the type of plate, then we do the butt welding. When we are doing the WPSS, we said that we have to go through all types of testing. So when we want to do all types of testing, how do you prepare the test sample? So to prepare a test sample, this is a submerged arc welded, butt welded piece. Now when we want to do the testing, then what we do is we prepare a specimen as required, and we prepare the whole plate. After preparing the whole plate, while collecting the samples, this is the procedure how we collect the sample. Because we expect that when you start the welding, for the first few millimeters, there will be a lot of imperfections or impurities. So you discard that piece. We collect the next piece. The next piece, we take it for bend testing. The other piece, we take it for the tensile testing. Then again, other piece, we have the bend testing. Similarly, this is a sequence. And in between, we cut a piece where we take the micro section. Micro section, we etch it, and we see it under the microscope. How are the grain parameters? So this is for micro section. Then again from the other side, we discard the other piece and then move inwards. So after taking out these components, what we do is, in the bent pieces, we grind this top off. Whereas in tensile pieces, we also try to grind it up. We grind up the top protruding portion, and then we have a piece like this. Now this goes in for the testing. So collection of the pieces is also done this way, and it is desirable to have it this way only. Then for the bend test, here I have shown the table from IS 2062. See, there are several types of steel. Depending on the quality of steel that we are conducting, and depending on the thickness of the plate, that bend test, this root diameter of the bend test, this mandrel is again specified, that what should be the minimum radius this particular specimen can bend. So what we have done is, here, this particular specimen, we want to do a face bend. In case of face bend, we have welded from this side, we turn the component and bend it from the other side. This is called the face bend. And this is called the root bend. Root bend means the direction. This is the side from which it has been welded, and the V preparation is from this side. So this is called root bend. Then side bend. Side bend means you bend it from this side. When you do the side bending, then also you have the radius, and these distances are also fixed. So these are the type of bend test when you are doing the, and this bend test, this IS 2062 specifies what bend test you should pass. Then in most of the components we have seen fillet testing. Fillet testing, how to prepare a fillet testing sample? This is how we make a fillet testing sample. So what we do is, if it is a flat position, it's a horizontal position, vertical overhead, these are the positions of welding. Let us say in this particular case, in the workshop, we have mostly flat position of welding. But let us say we have to do a welding at the side where you cannot put it flat. Maybe you have to put it horizontal, or you have to put it vertical, or you have to put it overhead. Then you have to qualify that welding on the basis of the position of the welding. Then electrode, what is the size of the electrode has been used? What is the fillet size it has been? Everything has to be mentioned. And accordingly, what we do is, we make the specimen, we have to hammer and break the specimen in this condition. And then we see the soundness of the weld, we see the extent of the fusion, we see the contours, and that qualifies the weld. So these particular testing procedures relate to welding procedure specification sheet, and when you prepare a specimen and you do all these tests, then it qualifies that you weld with the particular parameters and with the particular consumable, and in the particular position it has been welded, has passed the test. And further, this is transferred to all welding procedure specification sheets, and every component is then welded as per the welding procedure specification sheet. And all these documents are supposed to be given to the inspectors at the time of inspection and passing the welds. This is the welding procedure specification sheet. Why I am trying to show this is, we will see what are the effect of the voltage, current, where stick out if we do not follow this particular specification sheet. We have talked about the polarity. It's very important that we have seen your welding current. What is the type of polarity we have given? We have given it a reverse polarity. Why we have given a reverse polarity? Because our thickness of the components are 10 and 10 mm, and our welding rod is, welding wear is 3 mm. We want maximum energy to be bombarding here, and this particular component should melt rather than energy going from here and melting the electrode. What happens if the sufficient energy goes there and welding electrodes make? We have a very porous weld. So in most of the components, it is the DC type of power source we have been using. Most of the weldings are done in DC power source, and most of the welding in bridges are done in reverse polarity. If this is not followed, then we are likely to have very porous welds. here, this is the type of weld that is being done. Submerged arc welding. Here we have shown the polarity. We have connected the wire to the positive. That is, this is the DC electro, DCEN, DCEP, that is electropositive or reverse polarity. Then these are the joint details. Then these are the voltage current parameters which are supposed to be followed. And here, let us say we have a current with the, we have a current range of 400 to 500 mm for this particular component, and we have the sequence of 1, 2, 3, and 4. And then what happens? Suppose this is meant to be welded with a current of 400 amperes. We are expecting a depth and penetration of this. Somehow or other, if while welding the welder chooses to go down the current or increase the current, mostly welders tend to increase the current so that they can finish up the job and go early. Then what we have undesired penetration. That means the type of welding will not be desirable. There will be much more penetration than required. Then let us say we have the arc voltage. Arc voltage is normally between 25 and 30. We should not tamper with arc voltage. What happens when the arc voltage is high? As the arc voltage is high, the size of the weld increases and the consumable may go up. Then we have the electrical stick out. If the electrical stick out is more, we have lesser penetration and flatter weld, because more material will weld, more electrode will melt, but the depth of penetration will go down. So these are the parameters. And what are the effects if we do not stick to it? We may, let us say we do not stick to the proper electrical stick out. Maybe we have a bigger electrical stick out. Then we have a flatter weld and less depth of penetration. So these may land up into weaker mechanical properties. Then that is the welding sequence and technique. Run-off and taps, run-off and run-in and run-out. See, this is a very important thing, because what our observation is, sometimes actually it is required that when we are starting a welding from one end, let us say we are starting from one end this side, then when you strike an arc, initially it takes some time for the arc to stabilize. If you immediately start from the component, some length of the component will have maximum porosity, because the arc is not stable there. So a lot of defects will get accumulated. So what do we want? That our particular component, our weld should be defective. So what we do, we give a run-in and run-out. We give a portion of, we give a small portion of the exactly same of some small cut plates, so that we start the arc beyond the component. So by the time the arc reaches the component, it is stabilized. So position run-in and run-off has to be there. And if this is not adhered to, there are most likely that there is extremely likelihood that we will be having a defective weld at the beginning of the component and at the end where the arc is exiting, because there also it will create a lot of defects. So this is the run-in and run-out which is given. If you do not give this run-in and run-out, then the defect comes inside. So on both sides of the joint, we have to give run-in because the defect stays here, and run-out when the exiting, then the defect goes out along with this. So how do we test the weld? Once the welding has been done, we need to see that the weld dimension is proper. Suppose you have a 10 mm fillet or a 8 mm fillet, it should not be undersized. If it is undersized, then it will not have its proper mechanical properties. And if it is oversized, we have consumed a lot of consumables, and that is also not desirable. That has taken in a lot of heat input. So how do we do the non-destructive welding? We have several types: visual penetration, liquid penetrant test. These are the usual liquid penetration penetrant test is the most widely used non-destructive testing. So we have magnetic particle inspection, we have radiography, we have ultrasonic inspection. Radiography is mandatory when you are doing a butt welding, but when you are doing an ultrasonic inspection, yes, many places, many structures, as per my experience, are also accepting ultrasonic inspection for butt joints. Then weld joint dimensions, joint preparation, surface defects. So these are simply fillet weld gauges. So you make it as per your requirement, as per your this thing. You have individual fillet gauges, which you can have, which you can make many, which can be which can be available for at the time of welding for the welder and the inspectors. Then what are the surface defects that we see? We have surface cracks, there's crater cracks, incomplete root penetration, undercut, underfill on face groove or fillet, underfill of root, excessive face reinforcement, excessive root reinforcement, overlap. There are several defects that can come at the time of welding. Surface cracks are normally with dye penetration test. You can see crater cracks are there. That also crater. Whenever we do not desire that welding should have craters. The craters means once that particular point, there is a depression in the welding, so it doesn't have the right kind of dimension, so it may have a lot of stress concentration. Incomplete root penetration, there may be undercut. Undercut happens when your voltage is very high or when your current is very high. What it does, there is a fusion, but along with the fusion, wherever the weld starts, beyond that, a little portion of the plate has also melted where the welding has not been deposited. So undercuts are very dangerous. Similarly, excessive face reinforcement, groove or fillet or convex, that means where you have put excessive material, excessive welding material. Excessive root reinforcement, overlap. Overlap means once let us say we are welding up to a particular point, stopping and again welding, there might be overlap. Misalignment, you are going in one direction, up to certain point you have gone in one direction, then there has been a defect in your machine, then your weld has shifted. Then arc strikes. Arc strikes, you know what happens normally when we are doing this welding. Let us say we are doing it with a stick welding rod. So what we do is to test whether this is welding rod, welding machine is working all at once. We keep on, the welder keep on touching the components. So these are all arc strikes. Excessive splatter. Excessive splatter occurs only in case of a MIG welding. There is no excessive splatter in case of submerged arc welding. MIG welding, because we use normally carbon dioxide, and carbon dioxide, there's a lot of splatter in the mix. Splatter are very, very small droplets of weld which come out and they get stick to the nearby areas or fall into it, and they create a lot of defects. Excessive splatter is because of several reasons, whether the welder has cleaned the torch properly or not, or whether there is a defective flow in the gases. So there are many reasons why excessive splatter, that this is mostly relating to MIG welding. Warpage and distortion. Warpage and distortion, when there is a lot of heat input into the weld, more than the desirable, then the parent material warps or distorts. Then there are base material. The base material defects is again a defect of the particular base material, and this warpage and distortion is more prominent in stainless steel welding. Then weld size measurement, you have go no go gauges, and then which immediately gives you the then whether the weld is acceptable or not. These are the standard weld gauges, so in which you can measure all types of weld, but these no go gauges are for a particular dimension of weld. Then types of testing. Liquid penetration testing is the most widely used, and it's a very simple procedure. What is done is the entire weld metal is dye is given, which is normally red in color, and the surface is first cleaned, the weld surface is cleaned, and the dye is put on that, sprayed on that, and the entire thing is wiped up, expecting that whatever, if there are any cracks, the penetrant will go into the cracks. Then the entire weld surface is cleaned with a cleaner, and a white developer is put on that. The white developer has the ability to, if there are cracks and some amount of liquid has gone into the crack, white developer will pull it out and it will clearly show where the crack is. So liquid penetration test is very widely used to find out if there are any cracks or shrinkage cracks or whatever cracks in the welding. Then method of application, how you do it, as I explained, you can see here there are wherever there are red spots, that means the defect is there. The penetrant had gone in, and when the developer has put, it has come up. So micro etching, as I told you, when we are putting run in and run out, all the defects get accumulated there. So how can you do a micro etching? Where you can find a micro etching? You cannot cut a component in between. So we see the micro etching at the edge of the component. To see that, what we do is we grind that edge, we clean it with acid, and then we study it. It clearly shows the welding has got a different texture, the component has a different texture. I can show you. You see, in one first case, this is a very good fusion case. These are all images, photo images taken from micro etching samples. In the second one, the deeper penetration. That means what is the analysis here? What is the diagnosis? That particular welder has welded with a very high voltage. This is improper fusion. Improper fusion means either as I told you, when we are putting a DC electronegative or DC electropositive, there is a lot of bombardment into the plate. Our requirement is the parent material should also melt, and the weld metal pool is there. This is also molded, and when they fuse, they all fuse together. But in this case, the proper fusion is not there. That means only the weld material has melted. There hasn't been proper fusion or proper melting of the parent material. So this is improper fusion. This is also improper fusion. These are different. This is how it looks when you clean it with nitric acid. The edge is ground and cleaned with nitric acid, and this even gives you an indication how your fusion is. Then another welding is that is all about welding, the fillet weldings and the butt weldings. Then nowadays every girder, every plate girder, we do stud weldings for the RCA connectors. So stud welding is a process where you strike a arc. That the arc is struck to the stud itself. Here no filler material is used. You give a lot of current and try to. It's called a drawn arc. That means you put the component you put the stud on the component and you draw it. There's so much of voltage difference. There's a big spark. In that case, so much of heat is generated that the component melts as well as the stud melts, and then you press the whole stud, and both of the stud and the component, they fuse and they make a solid joint. So you have how you test how to do the stud welding defect. Typical fracture in shank of the stud. So if there is a defect, in the shank because the shank has generated more heat, then there will be a fracture here. Typical weld failure of the stud. This is the fracture line. So these are the different fractures. Studying on the fractures, we can find out what has gone wrong with the settings. Then there's a magnetic inspection. This also gives you the defects, the cracks because of the magnetic lines of forces. Where you put ferromagnetic material, all the discontinuous can be studied. Then radiographic examination. As you know, radiographic examination, you need a special power source, and these are normally outsourced. You have a film, you expose it, and you get the entire defect on the film itself, and the joint is exposed. The exposed joint to the radiographic source gives a total picture on the radiographic film. Then method and application of then ultrasonic inspection. Ultrasonic inspection, as we know, day by day ultrasonic inspection is becoming more popular. You have the ultrasonic rays going in, and then the defects that gets affected. Normally, the welding source that we use, as we decided, there are discussed that mostly girders use submerged arc welding and MIG welding. Manual metal arc welding is mostly used at the time of assembly. When we are assembling the component, we use manual metal arc welding. But when we are doing the continuous welding, it is mostly submerged arc. And where submerged arc cannot be used because of the short runs, there we use metal inert gas welding. This is the submerged arc power source. What we use are trolleys, and the power source and the controls. Normally, this is a MIG welding power source. We have basically to understand a little bit of power source. These are, let's say we want to particularly do a welding or in a workshop, we have to find out what is the power rating of this power source, and what is the current. Here the current is up to 400 amperes, and the voltage is this much. So when we have a specification of a particular machine, we can know for what type of welding rod or what type of voltage current parameter this machine is capable of. Accordingly, we select our machines. This is a new trend, and the RDSO specification now mentions that you must have an automatic eye welding machine, welding machine. What this machine does is it automatically welds and straightens the component, the flanges. When the welding of when the submerged welding takes place or any sort of welding takes place, there's a lot of distortion in the flanges. This particular machine, what it does, these are all submerged power sources, submerged consumables. It is welded on both the sides. Like this, the component comes in. So here the welding is done on both the sides. And at the same time, all the distortions are straightened through straightening rolls which are immediately there. It has one advantage. The advantage is when it is welded, the material is in very hot conditions, straightening is easy, and it can be done with lesser power. Normally, what other way is doing is to do the welding, allow the distortion to take place, and then find out methods of jacking, etc., and straighten these flanges. This is another automation and welding. This is a MIG welding power source, which is automated with the MIG welding tractor. Nowadays, there is a lot of automation which has come into the industry, and these tractors, etc., are very handy and very useful. This is a continuous MIG welding operation which is being carried out. Here again, this shows how this straightens. There's a top roll, there's a bottom roll. It straightens the flange when in a hot condition. It's got a lot of advantages, and the productivity is very high in these machines. This is what happens when you weld it. There is a distortion. Original position is this, or final position. What you do is this is exactly the mechanism that happens when we are doing it. When you want to straighten a roll, this principle is being utilized in that I-beam welding machine, but in a hot condition. In case you don't have this machine, or you can't straighten this in a hot condition, there are other machines also where the beam is taken, but here a lot of hydraulic forces are required to straighten this beam, because normally these flanges are of very high thickness, and it is almost impossible to straighten this if you have a cover plate. If you have a cover plate, then the I-beam welding, automated I-beam welding machines will not work, because the straightening forces are so high, those rollers will not be able to do it. This is a machine where it is cold straightening. I mean, after the welding has been done and the distortion has been allowed, then you take it into the machine and straighten it. Now let's come to stainless steel, because nowadays railways come into asking for stainless steel foot overbridges. So stainless steel is likely to be used more in bridges in the future. So let us say what are the type of stainless steel that are normally available. One is chrome nickel steel or austenitic 300 steel. That means we have 304, 316, 201, 202, 205, 216. These are the grades of chromium nickel steel. Another is straight chromium, the ferritic and martensitic steel. Ferritic and martensitic steels are used in many applications, but most likely not in bridges. In bridges, what we are likely to use is 304. 304 is 7 to 8% nickel and 12 to 14% chromium. This steel is weldable, and this steel is called, normally by stainless steel we mean 304, and in some cases 316. So what are the austenitic stainless steel and how weldable they are? Austenitic stainless steel is what we'll be using mostly in the bridges, not the ferritic or martensitic steel. So if you are using austenitic steel, as I said, 303, 304 are considered to be weldable, and so most of the bridges are likely to be done with AISI 304. Stainless steel is not as easy to weld as carbon steels. Carbon steel is easier to weld than stainless steel. The reason being, stainless steel has got the properties of stainless steel, it retains heat very easily. That means when we do the welding, a lot of heat is generated. Unlike carbon steel, which dissipates the heat immediately away from the joint, stainless steel retains the heat easily. That is why it can lead to warping and burn through oxidation. But stainless steel, when we are using thinner stainless steel, that is why you would never use thinner stainless steel with making DC electro positive. There, what we do is mostly thinner stainless steel is welded with TIG welding. TIG welding is not used in bridges. So this warping quality, that is the stainless steel mostly in critical operations are done with TIG welding, where the electrode is made negative and maximum energy is written in electrode and not in the job. But however, in thicker sections for our bridges, stainless steel can also be done with semi-dark welding and all other welding processes, but it is definitely a little difficult to weld as compared to carbon steels. So the types of welding that can be done in summer steel is exactly like this. We can make with FCAW or GMAW, that is gas metal and flux core, shielded metal or working. This is a very popular way of welding stainless steel because it takes into account all the defects, all the compositions, all the precautions at the time of welding. In case of summer dark welding, this particular flux which is used, we call it a neutral flux. Why you call it a neutral flux? Because in stainless steel, the major component is chromium. Chromium is the main component that gives stainless steel the properties of anti-corrosion properties. And chromium has got a very big affinity for oxygen. Chromium normally combines with oxygen, goes as a chromium pentoxide. So when we are using stainless steel, we should be very careful with the flux. It should not have any sort of acidic component or so, which can dilute the properties of stainless steel in the joint. So in case of summer steel arc welding, which is relevant to our bridges, the flux that we should be using, wear is normally the wear that is of the parent material or slight combination or different composition, but the flux has to be neutral so that we do not have any sort of loss of composition because of the welding. And let's come to tolerances. That was all for fabrication. What tolerances are expected in girder and fabrication when you are making different types of girders? So these are the tolerances, what is allowed. That there might be shrinkage tolerances, there might be out of dimension tolerances, there might be a distortion tolerances. The tolerances have the girder has to be within the required tolerance. So for a plate girder, so what is the tolerance which is accepted in case of overall length of the girders? How much is plus? How much is minus? So there are different type of tolerances. Distance between center of the bearings, plus or minus this much. Depth of the angles. Depth over the angles is this much, corner flanges. So different tolerances are to be very strictly adhered to. Then for holes, the tolerance of the holes is extremely important nowadays, specifically because earlier in railways, most of the girders were riveted girders. If there was a little mismatch in the holes, the hot rivet used to fill that, and the girders, the rivets used to take their load sharing in shear. But nowadays, we are having mostly HSFG bolting, and little bit of out of tolerance holes can cause to a lot of problems at the site because we do not have any scope of reaming or making bigger holes at the site, because that will completely change the load taking characteristics of HSFG bolts. Then welded plate girders, what is the depth? At times what we have is out of the square members, and what is the distance between bearings, assembled spans, everything has got certain limits and tolerances. So we should take all precautions so that we are within the tolerance of the fabricated girders. Then trial assembly. Once the girders are finished, then we come to the trial assembly. Trial assembly is equally critical, equally tricky. The reason being, the trial assembly, these girders, as I told you, are pre-staged or shortened component girders. That is vertically shortened, some places diagonally shortened, the top is, so that we have to fit it in such a way that we get the right kind of camber. because components of the bottom guard, if you check the length, it is supposed to have a higher arc length than the theoretical length at the time of assembly. So what is done is you first assembly the entire bottom end level. You bolt it in the entire bottom end level and put camber jacks at every node points. Then the other components are fitted. When you put the top guard, these holes will not match. What we have to do is we have to keep the pressure here and forcibly match these holes, because these are shortened components. These have to be given a lot of force to distort a little and fit into it. And after the bolting is done, then it is left, then you get the camber. So camber jacks are put behind under every joint, mismatching the holes, or if at all there, a little bit of mismatching, you can trim it here. 50% holes should be filled with drifts. If you don't put drifts, you will not be able to match, because by putting drifts, you try to displace a little bit of holes and try to take the component up, try to stretch it. So 50% holes should be drift, balance of the holes should be bolted joints. Then only you will get the camber. But without drifting, it is very difficult to assemble these girders if they are pre-stressed girders and if they are shortened component girders. So what are the dimensions to be checked? Dimension of the girder you should take. As you said, that tolerance dimensions have to be checked. Camber at node points to be taken with leveling instrument. And what happens after you assemble it? You have put joints, you have put supports on every joint, then you take out all the supports so that the girder is resting at the bearing points. Then you check the camber at the center and at the different node points, as has been mentioned, so that once the proper camber is done, then only the trial assembly is over and the girder is passed for the dispatch. Then another big component is the rigging part of it. Normally what happens in any fabrication shop, rigging is a very important part, because at times when we are doing plate girders, some of the girders weigh up to 8 tons, 10 tons. How do you lift it? How do you handle it in a workshop? So you have to lift it, you have to turn it, you have to topple it, because you have to weld it on 4 sides. So handling is a very important part. Normally it's done in a very unsafe way, and my advice to everyone would be, please know your lifting tools and tackles. Please know how your material, how your people are handling it, and what are the types of ropes you are using, what are the type of chains you are using, how do you study that. For example, let us say we take a rope, the specification is written like this. What does it mean? It means the diameter. This is a 1-inch diameter, number of strands has 6, number of wears per strand is 25, FW is standard pattern filler wear, EIP is extra improved plow steel. This is the grade of steel which has been used. This is, but these two components are very important. Then we have direction of the lay, right regular lay. Okay, this is the direction of the lay, that's all right. What is this core type? What is the core type? Independent wear rope core. That you also, in some wear ropes, you have wear ropes, some wear ropes you have hemp ropes. But whatever it is, this specification, after taking this specification, you can find out what is the load, this is breaking load of this wear rope, and what is your allowed load, what is the factor of safety, and what is the allowed load. Then, normally to lift component, we make splicings. Splicings are several splicings. Just check the rope, what splicing has been done. Let us say this is a hand spliced die. The first one is a hand spliced die. Second one is a mechanical spliced die, and the other two are switched and splitter sockets. We'll go one by one. Hand spliced means you open this strands and then twist it again, put and twist it. This is hand spliced. This is mechanical splicement. Both the wire ropes are brought here, and this is hydraulically placed. Swedging means this is a forged component. Wire rope is put inside. There is a conical sort of thing here, and you put molten zinc or molten lead into this, so that solidifies, the wedge is formed, and this is called swedging. So we have for different diameters of the rope, what is the efficiency of the efficiency means, let us say this one at 90% of its rated capacity, this will start slipping. So you may have an accident. So this is the splicing, the efficiency of the splicing. So mechanical splice die, what this is the efficiency, this is the rope depth. So Suez ropes or spelter or Suez ropes have almost 100% efficiency. These do not have, but normally we find people, rope is not there, they take up the rope and do mechanical splicing at the side, hand splicing at the side and start lifting. But when you're doing that, please be careful that you don't think that this will take more than 80% of the load, or even lesser is better. Then another point is how you put the rope. In my experience, I have seen that people think that just put the rope and lift it. I have seen accidents taking place when this angle is reduced. When this angle is reduced, the sign components become very high, very low. When the sign components become very low, let us say here is a comparison. Suppose you have a 60-degree angle, 45-degree angle, 30-degree angle. You can see that the multiplying component changes. This is a 100-ton, 100 pounds load. So each rope is supposed to take 500 pounds if it is a 60 degrees. So you multiply with the load factor 1.5, 1.154. That is the vertical component. That is the sign component. Suppose now it reduces to 45. This 1.154 comes to 1.414. That means this rope to take this is loaded more. Similarly, if you decrease the angle, the load still increases. So this concept that the lesser the angle that we make in this sort of lifting, the higher the load comes on the rope. And then another thing is when we are making a bend, let us say we are lifting a component and we are making a bend, then the diameter to diameter ratio decreases the efficiency of the rope. So when you are making a bend or when you're making through a round, then you have to be careful about the efficiency of the rope. Then the different type of spreaders you have. See, the question is now, depending on the component, you have to think about, or you have to choose the right kind of spreaders. Suppose you have a component which is about 8 tons and you put thin ones and put 2. Naturally, the component, the load on the spreaders, one of the legs becomes very high. Similarly, this is the rated capacity of different 4-leg spreaders. This is for a ready reference. Many manufacturers can give you. Kindly select the proper kind of lifting tackles from the manufacturer's recommendations. Otherwise, it may lead to accident in the software itself. Thank you.
Thank you, Mohanty Saab. One can clearly see why we consider you a master in your trade. It's not only science, it's also a specialized trade I think you have a lot of intuition when you do this work and you carry with you the sum total of your knowledge. It is so high and it is so diverse. To imagine all these things that you have to be alert about at all phases of fabrication. You've given us a real treatise on what to do and what not to do, what to look out for, where to be careful, and what there's so many things. You started from documents. You told us about documents, the 3 types of documents that we need to take into consideration. Then you talked about that's the QAP, the WPSS, and the WPQR documents. Then you talked about the various types of steel, the material properties. You spoke about the grades. You talk about the welding rods, the drilling, the types of jigs and templates, the steel process of cutting, the 4 types of cutting, and you talked about stainless steel, the do's and don'ts for stainless steel. You talked about fillet welds. You talked about the various types of weldings. You talked about the tests on welds. And you talked about the polarity issues that mostly for bridges we use welding with DC with reverse polarity to avoid porous welds. Then you talked to us about run-ins and run-outs. You talked so many points you actually brought out, which I think are amazing, sir, what you gave us today. Then you talked about gauges. You talked about the testing of the welds. You talked about the modern I-beam machines. You talked about that 304 is largely used today in FOBs. I know of a case in which we were somewhat involved as checking consultants, in which the stainless steel girder is actually distorted quite heavily Now I can understand why, because duplex stainless steel was used rather than 304. And in using that, I think there was a problem in the welding, and that all the girders actually distorted and we had to reject them all. So that was a stainless steel actually for live load with a road deck actually. So we had to reject them. Then you also talked to us about how the flux needs to be neutral, and the same types of welding procedures can be used for stainless steel, but we have to have a neutral flux. Then tolerances, trial assembly and camber, then the various fittings for rigging, the tools and tackles, the spreaders, the load factors, and the ratio of D by D on the rope, the diameter ratios. You gave us so much information today, sir, for which we are very grateful and very thankful. And I think those of us who are structural engineers and who deal with bridges, I would say, these are the things that we actually are never taught. These are the things that we simply do not invest our time to learn much about. We see 2062 as a code and that's about it. But what goes into the nitty-gritty of actually the process of fabricating a truss and the various components of the truss are what you brought out today. And I think we have all been educated by you. We've all learned a lot from you, sir. Thank you very much. Thank you very much. And I can tell all of you all in the audience that at some point in time, if you ever happen to be in Odisha, please do visit his facility. It is an amazing facility that he has. With that, having said that, I think there are I don't know if anyone in the panel would like to say a few words. Ravindra, would you like to say a few words to start with? Ravindra Goel, would you like to say a few words, sir? Yeah, go ahead, Ravindra. Ravindra, we aren't able to hear you. So then can I ask Mr. Pandey to say a few words? Mr. Pandey?
Yes, yes.
Go ahead, sir.
Thank you very much, Mr. Mohanty. It was quite elaborative and very knowledgeable session. You started with the entire gamut of welding parameters, cutting and assembling techniques. And I hope that entire participants must have taken note of it, and they must have been enriched with your valuable experience and input. And once again, I thank you for sharing your experience, and thank you all participants also from JSW side. We thank all the participants and Mr. Mohanty and all panelists. Thank you. Thank you very much.
Madam Singh, would you like to say a few words? Otherwise, can I get Ravindra back? Ravindra, are you back with us now? Maybe he's not. Okay, let us take some of the question answers that have come up, Mr. Mohanty. Let us take some of the questions. Okay.
Okay. First
If
is
you look at the
how can we?
questions,
Yeah, I'm just. First
Yes.
is Mr. Bhutani. He has asked, how can we check the yield stress of weld joint, butt joint or fillet joint? Well, Mr. Bhutani, I showed you the sample specimens that we have done, and on that we can go into the universal testing machine, standard testing procedure that is done for the plate. What we do is we do the weld, then we grind it up. Then it's like any joint, any plate. Let us say we consider a simple plate. Then we go to the universal testing machine and carry out the yield stress tests. A standard, the Young's modulus graph that we generate, from that we can find out the tensile and the yield stresses, or the yield. For the yield also you can find out from there. It's a simple tensile testing procedure. Please explain how to fit fillet size in case of SMW and FCAW process of I6M welding. How to fix fillet size? I think the question says how to fix the fillet size. I think the fillet size is fixed at the design level.
the design.
At the design level, you fit the fillet size, And we have to achieve that fillet size with proper voltage, current, wear speed, and wear fit parameters, both for SMW and FCAW, if they are automated. If they are not automated, then there is an element of component on the welder to achieve the fillet size with the right kind of wear, right kind of the flux.
That's
What
Mr.
else?
Bhutani, yeah? Mr. Bhutani's question, yeah.
Yes. The third question is, butt welds can also be full strength butt welds. Then why they are generally not allowed if it can save a lot of wastage?
Just let me say that I think this must be Mr. Veer Deshpande, who is an extremely good structural engineer, one of our foremost bridge engineers, if I'm not mistaken, and from Stratcon, a very famous consulting firm. If it's the same gentleman, these are the questions being asked. Yeah, go ahead.
Then why they are generally not allowed? It can save a lot of wastage. Butt welds can be full strength butt welds. Yes, in some components, I have seen that butt welds are also allowed instead of fillet, and they are also tested with ultrasonic testing. But in welding, mostly we have not adopted that in bridges, and we mostly go for fillet weldings, mostly for fillet weldings. But I do not know in future if you are going for, because in certain equipment manufacturing, I have seen the German drawings. They are giving full strength butt welds, and the procedure of testing is also ultrasonic. But in bridges, we have not adapted that. What is the size of notch for making weld samples, whether partial penetration or full penetration welding? This is again the notch, the particular specimen depends on what your codal provision provides. So that must be taken from the proper code. Is run in and run out required even with CNC machine? Yes. Even with CNC machines, the run in and run out, the purpose of run in and run out is to contain the weld defects much before the actual welding on the component starts. So there is no CNC machine for welding as such. Yes, there are CNC machines for cutting, there are CNC machines for drilling. Welding doesn't need any CNC. CNC is basically a computerized numerical control machine where you have a feedback mechanism for the accuracy of the positioning. In welding, we don't have any accuracy of positioning. So these are not CNC machines. CNC machine is not required. Maybe at the best, you can go for a PLC for automation purposes. We don't have CNC machines in welding. And whatever machine you use, it is only for controlling the defect that we need run in and run outs. So it has got nothing to do with the machines. I think these are the, another is there. From where you get the tolerance limits. See, I'll tell you the tolerance limit that I showed you is the tolerance limit that is available in IRS B1. If you want to see, you can take IRS B1 code, and all the tolerance limits are made there, and we have mostly adopted that also in our IRC code, IRC B5 committee still this code.
Very true, sir. So those there are some more questions, sir. You can see there are some more questions.
What are some of the safety measures that an engineer contractor need to monitor on site when fabricating rating steel members on site? Here, safety is a very important parameter. Let us say when you are trying to fabricate it at the site, first of all, you must see what sort of material handling equipment you have. What sort of, normally in India, we use hydras. It's a popularly used, we call it hydra. That's a pick and carry crane. But my experience working with some of the international companies in erection, they do not rate hydras as a pick and carry crane. For them, a pick and carry crane is a forklift. We don't use forklifts very frequently here. They don't use any equipment like this in Europe or in America. So they use hydraulic cranes or bigger cranes. First of all, check what sort of crane you are using, because in my experience, hydra is a very unstable equipment. I have seen a lot of hydra toppling at site. In fact, earlier you used to use a hydra where the operator used to sit at the back. Now, in most of the big companies like Tata Steel, etc., they have banned those machines. They have given a concession of the world of the operator sitting in the front is a new type of hydra. But anyway, hydras are used. First, check the lifting equipment, your lifting tackles, and then all the procedures that you need. Well, when you are fabricating inside, ensure one thing. Ensure that when you are doing a MIG welding, you must cover the space so that the carbon dioxide doesn't get blown away. Because carbon dioxide is the shielding gas. If the carbon dioxide or the shielding gas gets blown away, you'll have a lot of blowholes and porosity. But in case of summer, that it makes no difference. See that your welding is covered so that it doesn't get affected by sudden rain or any other local climatic disturbances. In case of erecting steel members, then I must tell you that you must totally go for the procedure of crane and the crane manuals, where to position the crane, where to lift the component. You must check the stability of the crane. You must check the stability of your harnesses. There are n number of components. If that is a safety and handling is itself a subject.
Go ahead, sir.
Another is what rectification for defects in weld. Well, when you have a defective weld, you don't reject it. What you do is normally you grind off that defective portion, remove it from the parent metal and re-weld it. I think that is the question. Sir, what advantages of preheating before welding? Well, preheating, I tell you, preheating is done because of two things. Look, why do you preheat a thing? So when we are welding and the heat gets dissipated too fast, then the welding, the weld bead, which is in a molten state and is cooling off slowly, it undergoes through a lot of stress and it cracks. And moreover, preheating is required because I told you, because as we were discussing, we told that when the carbon equivalent is more, the heat transmission, the concentration of heat, those parameters change with carbon concentration. That is why a higher carbon equivalent, that means steel with higher carbon equivalent, needs preheating. The basic purpose of preheating is to see that the weld metal doesn't cool off that part, or that doesn't dissipate the heat to the nearby places, and thereby affecting and putting stress on the weld. Any event where camber was not able to be achieved, what decision taken, your experience? Look, sir, if camber is not achieved, my experience is we manage things, but it should not be done. I'll tell you the present one erection we are doing today. Look, earlier we have done cantilever erections when we are doing that is incremental cantilever erections for through girders. In many places we have done. In that case, what we did is we used to do the riveting and go ahead with it. But today, when we wanted to do it in a bridge, we were dissuaded. And there are reasons for that. What happens if you see in a cantilever erection, when the girder is in cantilever, the components are in a different stress conditions. And if we mash the holes, we are not able to pre-stretch. Then the whole joint, which is with HFCI bolt, doesn't behave properly, and there is a tremendous loss of camber. So doing cantilever erection in the bolted girders nowadays, for these through girders, I think the experience is not good. We usually have a loss of camber. So prefer to have little precaution for the camber.
In the sense, sir, would it be, what would you advise? How can you take a precaution like that? In the old days, of course, I would say
see, what was happening was, see, when you did the riveting of the hole, whatever the tolerance in the hole is there, if there is a little bit, we could fill it up.
Yes.
We could fill it. Nowadays, the entire load is transferred by friction. So any loss in camber becomes very deadly for the bridge itself. It keeps on losing very fast, and the desirable camber we are not being able to achieve because of the type of load that is on the bridge. See, when we are doing as we discussed, as we are doing in case of a trial assembly, we are giving support at each joints, each camber jacks, and then trying to lift it and fit it. And through this drifts, that is not possible when you are doing it in this case now. And the usual experience is, as per the field people who are doing it both from the railway side and this, preferably we should do these bolted joints with a little bit of support from bottom. I do not know. Maybe we have to discuss it a little more.
I think so, sir. Because something like this, it will affect all our railway bridges, would it not?
Yes, it is. It is. I am thinking what is to be done now. Is there any other method how we can?
We will. I hope Ravindra Goyal is listening, Chief Engineer, Western Railway. We will ask him for his comments after this, sir. Go ahead. Next question.
Can you visually identify the E350 plates as the oxidized layer on the top of the killed or semi-killed plate? Is it corrosion resistant? Can you identify E350A, BR? No. You cannot do anything of that. See, you have asked about killed and semi-killed. The concept of killed and semi-killed is very simple. See, this is a thing which is related when steel making is going on. When steel making is going on, basically a little bit about the chemistry part of it. What we do is to clear the dissolved oxygen, we try to blow carbon monoxide inside the steel. The carbon monoxide just comes out, and by the time it comes out, some of the the steel solidified and some of this is trapped. That is called semi-killed. But what happens in case of A and BR or BO, grade A, BR or BO or grade A, what happens? Those, after melting of the steel, it is cast into slabs. Then the slabs are taken and heated and rolled into plates. So what happens whenever the defects are there, during the time of the rolling, they almost get flattened and comes into one, it becomes solid. The defect gets rectified. But in case of C, where you have to do a Charpy at -20°C, you cannot take that chance. You cannot take that chance. So what you have to do is basically what we need to do is we need to do the killing. In killing, what they do is they put a chemical into it so that there is no question of oxygen getting trapped. So we know, we have seen from the IS 2062, in case of grade C, only killed steel is used, and you have no chance to see whether a steel is killed or semi-killed. You also cannot identify what is 350 BA, BR, or BO visually. Only thing is that if you want to find out A, BO, or BR, that is only by Charpy. Because chemical composition is almost the same. So only the Charpy can tell you it's BR or BO. Why our bridges and HSL a high strength, low alloy steel? What are the challenges choosing the filler material? See, we can go for it, but question is the price part of it. We can, and filler materials are many filler materials, and there are a lot of companies that can use the high strength, low alloy steels can be used, but then again, the cost part of it and the availability part of it. Why are there major observations that you noted while inspecting a bridge are some years after, especially with respect to bolts and welds, and how they can be avoided from start? See, this is a very vast question, because every bridge needs a special study. We cannot generalize it, but to be little bit specific, welds you cannot rectify, At the site, welding of the brace should be avoided, because by that time when the brace is erected at site, it has started taking its dead load. Already the components are loaded. If the need is really high, then you have to take a chance at welding, and preferably don't weld it at site. But if there is no other way out and the welding is cracked, then maybe you have to also weld the brace at site. Bolts, if there are bolts, because bolts can always be replaced, and how they can be avoided from the start. They can be avoided if you take the precautions at the time of fabrication, proper welding, proper inspection, then the welding will stand definitely. And bolting, you at the time of your trial assembly, please ensure that your bolts match properly to the holes. In case you have a lot of defects, it will be very difficult to avoid the mismatching and a lot of reaming and loss of camber, and then snapping of the bolts. A lot of things can crop up at site if you do not take precautions, and if you do not identify the defect at the time of assembly and try to rectify it at the shop level.
Right. Thank you again.
One more question.
One more, I think. Yeah.
CNC welding drilling machine that are shown are used to fabricate the fabrication units. Where is it? However, site for drilling and welding. Okay. See, welding in sites, many people use submerger, many people use MIG. There is nothing at site you can do. But if you want to go for automatic beam welding machine, then you have to make a temporary workshop at site. If your project can handle that, then you should go for it. As for drilling, yes, CNC drilling machines are very common. The machine doesn't weigh more than 5-6 tons. You can take it, make a set and put it at the site if you can afford to. If the project doesn't permit you, don't put a CNC machine. You go with your magnetic drill bases. You can go with radial drills. You can go with manual drilling. But in case you want to put a CNC, nothing holds you back. You can do it. But then again, your project should be able to take the cost. That's all. That's all I think.
Thank you. Thank you, Gyana. Your mastery shines through. Your art, your knowledge, your mastery just shines through. There's no question about it. Thank you very much, Gyana. Thank you to JSW again. Ravindra is unable to join us because he's traveling at the moment, but he can hear, but he can't join us. Otherwise, I would have very much welcomed his comments today. We miss him today. Thank you to all the participants who have so patiently stayed back. I think we have learned a lot today, and these notes and these handouts will all be made available to all who have been registered participants. You will get all the notes and handouts. I have nothing more to add for today. I think it's time to bid adieu. Unless anybody in JSW want to say anything, Vinay, anything?
No, thank you.
Can I close? Okay, and on that note, ladies and gentlemen, let us pause for the evening. Let us go and have a little break now, a richly deserved break on a Friday. And see you again next month for the day 4 lecture, which will be on the next month, and we will keep you informed of updates. Thank you, and
thank you.
Have a pleasant evening. Have a pleasant evening. Thank you very much.
Thank you.
Thank you.
Thank you.